back to this. I don't know how we got there. Quantum. What is quantum and quanta? Okay, a quantum leap, I erase this, is when an electron jumps from one energy to another. That's called a quantum leap, when it jumps from one energy level to another. So what is a quantum? What is quanta? What do you think? How does it jump? It has to do this. It has to gain a specific bundle of energy. That's what a quanta is. Quanta. So that it's a specific amount or bundle of energy. So quanta technically is kind of like the plural version of that. So multiple units, multiple specific amounts of energy. Quantum is just for one. But yeah, that's the amount of energy it either gains or releases. So when an electron gains or loses energy, that's how much it'll lose. It'll lose a quanta or a quantum, depending on how you word it. So that's what it's all about. And there are dual properties of the electron. We talked about the double slit. So electrons act like particles sometimes. So like when it's jumping around, it's acting like a particle, but it's releasing energy, and that creates light. So electrons sometimes kind of act like light as well. They have wave properties. So in that equation, the wavelength and frequency really are the wave properties of that. Okay. So questions about any of that before we move on here? All right, I'm going to show you a bunch of stuff on here. So lights, please. Keep your notes out, obviously. Let's make it nice and dark here, guys. Easier to see. More fun. Earl, help us out here. Earl. Take your time. No need to rush her. Yeah. Slade, you can help too. Let's go. You guys moving next door, you're all moving it up. Alright, so this is just kind of reiterating what I was talking about. So again, you got your radio waves, wavelengths. So a wavelength is times 10 to the 4th meter sticks, right? That's humongous. That's a giant wave. Okay? Gamma rays times 10 to the negative 14th. Visible light is the only part we can actually see. Right? We can see visible light. We can't see any of these other ones. Okay? So that's the part we really focus on. So if you end up learning how to use these equations, which you will be today and tomorrow, and you calculate a wavelength 450, that's a blue. You know that's going to be blue. That's a blue light. If it's a wavelength of 750, it's going to be red. All right, so that's kind of where we're headed. So that's just a kind of a visual for you, another way to see it. The distance between the wavelengths here, red are bigger wavelengths, violet smaller wavelengths, and it kind of shows the progression. Gamma, cosmic rays are really close together. Microwaves are, you know, kind of in the middle-ish. Well, I guess that would be the middle-ish that are visible. But anyways, that's just another visual for you. You should have a general concept of what's going on here, okay? Even though we focus just mostly on the visible. All right, so that's the electromagnetic spectrum. And what does that word electromagnetic mean? It means these waves have two types of properties. Just break the word down. Like electric property, electricity can affect these waves, and magnetics can affect these waves. Magnets, magnetic fields. So electric fields. So if you pass electromagnetic radiation through electric fields or magnetic fields, you can kind of affect those waves. That's what that means. Okay. This is what we need to really be cognizant of. In our notes, we're going to write down for hydrogen. Let's write this down here. Hopefully you can see if I write some stuff down. Where is the... So for hydrogen, which is the only thing we really focus on, visible light comes from the Balmer series. Balmer series. And that's this one right here in the middle. And that, put a little star here, is when we have electron transitions from, and if you look at the energy levels, N2, 3, 4, 5, and 6, we're not going down to 1. So the Balmer series is electron transitions from N equals 2 and higher. So N is the energy level. So if we have an electron falling from the 6th energy level down to energy level 2, that gives off light with a wavelength of 410. If it's from 5 to 2, that's 430. From 4 to 2, it's 486. From 3 to 2, it's 656. You don't have to memorize those numbers. We're going to be calculating that stuff. But that's the visible light that we can see. So I believe one of these, I don't want to guess, I have it on the next picture here, but these other ones are different types of light, different types, it's not visible. You know, X-rays, for example, different types of electromagnetic radiation. So when electrons fall back to the ground state, which is interesting because 2 is not the ground state for hydrogen, right? 1 has 2. So we say ground state because if the electron started on the 2nd level and then, you know, somehow it's on the 2nd or right, and then you excite it more, then it falls back to number 2. That's technically what we mean when we say ground. It went back to its original location. It doesn't necessarily mean the ground state for hydrogen. I know that's confusing, but again, the Balmer series is what we're going to be talking about. That's visible light. And I think this one explains it a little better. I don't know if you can read all of it. Ultraviolet is the Lyman series. Balmer is visible. Infrared would be Posh and Brackett. I've never heard of the P fund, but I've heard of these other ones. So that's the Lyman series is when it comes back to N equals 1. Balmer series is when it comes back to the 2. Posh and 3, Brackett 4. So it all depends with that one electron in hydrogen where it starts and then it comes back to that. So if it starts on 1, jumps up, it comes back, that would be ultraviolet light that it's giving off. It starts on 2, comes back, that's visible. Do you really need to know all of this? No, I'm just giving you an overview that we're focusing on just the Balmer, the visible. And remember, just hydrogen. We're only dealing with hydrogen. So these two videos explain emission spectra and absorption spectra. So emission spectra would be emitting means what? Giving off light, and absorption means absorbing light. Right. So there's two types of spectrums, and they're both actually in the back there. But I think it's good for you to see these and listen so that you have a concept before we move on. So again, why are we learning this? What are we talking about here? Understanding the electron transitions, giving off light, and then those two equations, how they relate to it. So I like to explain what we're doing first, then use the equations, so you're not just doing the math and not understanding what the heck you're solving for. So that's why we're doing this here. Okay, I doubt the AP test is going to say, explain emission spectra. They're not going to do that. Okay, that's too easy of a question, but you should know what it is. Oh, I guess there's no sound here. I thought there was. The next one has sound. Okay, so this one's just explaining or showing an animation. So E equals HV. If it gains enough energy, right? E equals HV, so the HV would be the energy. So it gains the energy, they're going to show it jumping up to a higher energy level. So that's the excited state. Once it jumps up to the higher energy level, this is pretty slow, but it's a good visual. It's unstable. Why is it unstable? Why is that unstable? That's a good question. Nobody's got anything for me? That's unfortunate. In chemistry, what's the overall theme of everything? Stability means what? Earthquake. When an earthquake's happening, are things stable? No. Is there a lot of energy being transmitted and transferred to everything? Yes. So in chemistry, it's the same concept. When things are not stable, that's because they have a lot of energy. When they are stable, they have less or low energy. Right. So when an electron gains energy and jumps up, it has more energy. It can't live up there. It's too excited. It has too much energy. Okay? It has to come back down to where it originated. So it has to get rid of that energy in the form of light. That's what this is, a wavelength which is the same amount of gain. Remember, that's important. Same amount that it gained, so it falls back, and now it's more stable again because it doesn't have that energy. So low energy means stable. That's the theme for a lot of things in chemistry. Low energy means stable. So yeah, it emits a photon of light. Again, the wavelength properties there. The light hits you in the eyeball. All right, so that's visible light. I don't know where else they're going with this here. Okay, so if we give it more energy, I would assume, I haven't seen this in a couple of years, I don't watch these very often, but I would assume if they're giving it more energy, it might get crazy now. What's it going to jump up to? 3. The 3rd, right. Whoa, getting crazy here. Okay, so we're jumping up to 3, and it looks like it's going to fall down, and it's probably going to give off violet light. So from 2 to 1, it was less energy, so that's red. That is, in general, less energy with the red colors because that frequency is small. I mean, yeah, small. But then when it goes to purple, violet, it gives off closer wavelengths. So there's a little bit more energy associated with that. Okay, so that, I probably could have skipped that actually, but I mean, it's a good visual. And then this one is a video. I'm pretty sure they explain a little bit here. If not, it's just some music for you, Dylan. All these videos have strange music. What? So, I'll turn it down a little bit. I don't know what's happening. But, so, light is given off from the star and it has all of them. So, our sun has all of the colors in it, right? But, remaining photons in the atmosphere are detected on Earth. So, some of it might be absorbed by the atoms in the atmosphere because it literally hits them. That's interesting. Yeah, this guy's freaking me out. I don't know if he's trying to explain it or what. Chemistry, emission rap. So yeah, so atomic. The point is to see the difference between emission and absorption. So when it gives off the light, right? They're excited, and they give off the different photons of light. So depending on whatever element that is, depending on the amount of energy here, all right, it's not picking up those other wavelengths. It's just picking up these 3, the bright line emission spectrum. So that's like those tubes you saw last year. Okay, you looked through the spectroscope and you saw the different light that was coming off, but it was specific wavelengths. Absorption is different. So you give the electron some energy, maybe with some light. So you give it some energy, moves up. So now it's up from where it was. It was in the ground state. Now it's on the, we'll say, 3rd energy level. More of the same, it gives off that energy. Gives off that energy in the form of light, certain wavelength, depending on how much energy that is. Thought they were doing absorption. Why didn't you show me absorption? What the heck happened? Okay, I guess that's not the one I thought of. That's all I got. No, we're not going to watch that again. That was bizarre. Well, this guy's good though. Maybe he has a. I just want you to see the difference. All right, here we go. I'm done with that. Something else is playing in the background. Okay. So here's what I want to show you. Okay. So this is absorption. This is emission. So if you ever see anything like this, so all of the wavelengths of light are present, but the element, compound, substance, whatever it is absorbing specific wavelengths of light. That's why it's black, because it's not emitting those colors, it's absorbing those wavelengths. So that's the difference between emission. This is what we talk about most of the time. But absorption, and it's on the back wall too, is when it absorbs the energy instead of the light instead of emitting it. So I just want you to see it at least once. That's what absorption looks like, and that's what emission looks like. So what is the point of all this? A concept of when we're using those two equations, which we're going to get to here in a minute, what's going on, okay? All of this is happening, depending on the question, depending on the light, depending on the energy, depends on the wavelength that it produces. So let's get to some sample problems here. All right, lights please. All right, so we got those two equations. E equals HV, C equals lambda V. So let's explain the constants. Take out your equation sheets, please. Go ahead, let the sun back in, guys. Now let's make the computer possible. Look, it's dark. Okay, so E stands for energy. V stands for frequency. H is Planck's constant, and that's on your equation sheet. Planck's constant. C is the speed of light. V is frequency, and lambda is wavelength. Now, we have to understand units as usual. So go ahead, copy all that down. So we'll talk about E equals HV first, then we'll talk about C equals lambda V. And then I'll give you some practice problems and, of course, homework. Okay, so what is, I don't know if it tells you in your equation sheet, it might. Well, it tells you what Planck's constant is. So let's talk about E equals HV first. What's H? What is Planck's constant? Give me the number and the unit. Pat, go ahead.
Uh, 6.626 times 10 to the negative 34 joules.
Joules per second?
Yeah.
Or joules times second?
JS, times second.
Joules times second. Okay. Good. Now that's Planck's constant. That's H. That's a constant. Now V, does it give you the units for V in there? All right, physics people?
Hertz.
Hertz, but we're not going to write Hertz. We can. You can, but I'm going to write what that really means. Anyone know? Steph, what's frequency? Remember what I was saying over here? With that waves that pass a point in a certain second, right? So the frequency here, you can write Hertz, but we're going to put S minus 1. That means 1 over seconds. That is Hertz. So 1 over second is Hertz. Same thing. Or S minus 1. S minus 1 is the same thing as 1 over S. Okay. So what is the unit on E? Energy. If you do joules times seconds minus 1, which is really joules times seconds times 1 over S, what cancels out? S. So I'm just, I wrote equals twice. So I'm just stressing that this is joules because this has to be 1 over seconds or Hertz. This has to be joules. This is the same. That's a constant. Just keep that in mind. That always has to be seconds to the minus 1 or 1 over seconds or Hertz. It all means the same thing. Now, why is that important? Let's come down here. Speed of light. So C equals lambda V. 3 times 10 to the 8th meters per second. If frequency, right, so this is here, if frequency is S minus 1, what does wavelength have to be in? Meters. That's a huge problem because light waves are so small. What do they usually give you the unit in? Nanometers. So they usually tell you nanometers. Does anyone know the conversion from nanometers to meters? 1 nanometer, one meter equals lots of nanometers. Yes. Is it on there by any chance? So it should be 1 times. Hold on. I always forget this. It's either 1 times 10 to the negative 8 or negative 9. Give me a second here. I believe it is 1 times 10 to the negative 9. So 1 nanometer, 1 times 10 to the negative 9 meters. So again, the whole, every other year I get rusty. I always get some things confused. So that, obviously I will remember now, but you need to also memorize that. So 1 times 10 to the negative 9 meters are in 1 nanometer. You could flip that, right? You could say there's 1 times 10 to the positive 9 nanometers in 1 meter, whatever you want to use. But that conversion is important because a lot of times wavelength will be given to you in nanometers, and if you plug that in here, you're not going to cancel out, or you're not going to get meters per second. You're going to get nanometers per second, and that doesn't make sense, right? So it's got to be meters. So that's the key. All right. So again, what are these two used for? The energy associated with electron transitions. So let me give you a sample problem. We'll start off with a simple one, I guess, ish. Calculate the energy of a photon with a wavelength of 510 nanometers. Calculate the energy of a photon that gives off light with a wavelength of 510, or that has a wavelength of 510. So calculate the energy of a photon with a wavelength of 510 nanometers. So again, what is a photon? It's a little tiny particle and wave of light. So an electron gains energy, it falls back to the ground state, releases energy. It releases that energy as photons. So they're saying you have a photon here that's given off from that transition and it has a wavelength of 510. Tell me how much energy that photon has. So you have to use both equations here. E equals HV and C equals lambda. If you would like, you could combine the two equations to make one big equation if you want. Since they both have frequency in them, you can combine them. It's up to you how adventurous you want to get here. Exciting day in chemistry here. Too risky. You know what I forgot? I'll have to do it tomorrow. tomorrow, I don't know what happened, so I'm moving my stuff around here, cleaning my desk. I wanted to finish going over your periodic trends. We'll do that tomorrow. The answer to this, and then your homework quick. Anyone get an answer? 3.9 times 10 to the negative 19.
Yay.
Don't worry, you have more practice right now, or for homework. Chapter 7, number 9. Chapter 7, number 9, 17. 917, 95, and 138. So only 4, no big deal. And 138 gets a little tricky. Usually does. Something to do with moles, I think. I will be after school. I don't have a meeting. If you need help with anything in the lab, I'll be after school.